Welcome to Let's Talk Energy. Let's Talk Energy is a production of the National Energy Technology Laboratory. The Energy Lab is one of the U.S. Department of Energy's 17 national labs. Your host is Joe Culver.
We've brought the Let's Talk Energy cameras to Albany, Oregon this week, to the National Energy Technology Laboratory's Research Center here in Albany. And we're talking today with Dr. Omer, who is a materials scientist. Thanks for being with us today. Now you're using computer simulations to help develop and design special materials, is that right?
That's correct. We use computer simulation and modeling to help design new materials, new alloys to be used in the new energy conversion technologies.
That's a good thing to bring up because the National Energy Technology Laboratory, which we call the Energy Lab because we have such a range of energy programs, our mission, our focus is energy. So how do these materials relate to that energy mission?
It's a good question. And in terms of the fossil energy, if we focus on the fossil energy, there is limited amount of fossil fuels left to be used, and public is demanding that we use this fossil fuels in a responsible way, in a clean way. So the scientists and the engineers are developing new technologies, cleaner and more efficient fossil energy conversion technologies to be used in the future. One of the most significant barriers in developing these new technologies is the lack of materials, appropriate materials for these technologies. And in order these technologies to become a reality, we have to come up, we material scientists have to come up with new materials that can operate at higher temperatures, and these materials are being currently developed in different laboratories, and including the National Energy Technology Laboratory.
There are a lot of materials that we have in the world today. Why do we need these new materials? Now you're talking about, I think, hotter environments as part of it. Why do we need to run the plants at a higher temperature?
In order to run these plants more efficiently, we have to go to higher temperatures and higher pressures, and that is the reason we have to operate these plants at these more extreme environments in order to get more efficiency out of them, and the new technologies are focused on this issue.
We were talking to one of the other scientists here, Dr. Paul Jablonski, and he was talking about materials that would operate in plants that are running at about 700 degrees or 800 degrees as opposed to 500 degrees. So we've got a jump, let's say, of 200 degrees. The materials that we have now just won't work at those temperatures. Is that correct?
There are two ends of the spectrum when we talk about the high temperature materials, structural materials. One is that the lower end is the new technologies such as ultra supercritical power plants. They are being developed and they require materials that are going to operate around 760 degrees C. Today, some materials exist to work at this temperature level, but there are materials that are too expensive for this application. So we need materials that are going to be operating at higher temperatures, but also not as expensive as, for example, nickel-based superalloys that are the state of the art of today. What is happening is today's plants are using different kinds of steels, ferritic steels, austenitic steels. The next generation ultra supercritical plants are going to be running at much higher temperatures than today's plants. Therefore, the steels which are being used today are not going to be sufficient. And again, the next class of materials which are available commercially today is the class that is the nickel-based superalloys. And as I said, those are a little too expensive for this ultra supercritical steam plants to be applied.
Dr. Dewan, Dr. Jablonski was talking to us about some turbine materials and things for these ultra supercritical plants. Tell us how your work, what is the role of your work in this?
I am a material scientist, and I work with a group of other scientists who are also material scientists and computational material scientists to develop new materials that can operate, that can be used at higher temperatures. The need for these materials is there as we develop new technologies, new energy conversion technologies, such as hydrogen turbines, such as oxy-fuel turbines. These new technologies, new turbine technologies, are predicted to operate at temperatures that in which there are no materials, there are no structural materials to be applied, and so our goal in this lab is to develop materials based on refractory metals. And then these refractory metals are the metals like chromium, molybdenum, niobium, tungsten, and these metals have very high melting point and very good strength at higher temperatures. But also they have their problems, and we have to overcome these problems, solve these problems in order these refractory metals to become a material, a commercial material for these new technologies.
These refractory materials, one of the issues I understand we have with them is a lack of ductility. Mm-hmm. And so you're working with them. Are you making them more ductile?
That's our goal. One of our goals in developing these new materials is to improve the ductility of these refractory metal-based alloys. And how we go about solving this problem is we utilize computational techniques to get an understanding into these materials, and then we design our experiments and do experimental work. And so we work with a combination of computational work and experimental work in order to speed up the development of these materials.
You've talked about ductility quite a bit. Just what is ductility?
Ductility is a materials property that gives the material the ability to deform, and so ductile materials we can work with, we can shape them through different metallurgical processes, but if they lack ductility, the materials are not easily deformed.
Is ductility kind of the opposite of brittleness?
Exactly. It is the opposite of brittleness.
So if it's a brittle material and you tried to form it into a shape, it would snap. But a ductile material means that you can bend it.
It can bend, right.
Okay.
Exactly.
What is it you do to a metal that increases its ductility?
There are different ways of approaching that. One way is we can alloy a metal with different elements and increase its ductility. Another way of increasing ductility is applying different heat treatments to it, and we can do that and increase the ductility. So there are different metallurgical ways you can apply in order to increase the ductility of a metal.
What is a heat treatment that you could apply? What does that mean?
Heat treatment is a process that involves heating the metal piece to a temperature where you know how the metal is going to behave, and cool it down to and hold it up that temperature a certain length of time, and then bring it down to room temperature at a certain cooling rate, and in order to obtain a desired microstructure.
Going back probably, gosh, as far as sword makers and alchemists and a lot of things throughout the history of materials development, people poured two things together and saw what they did, and then maybe they added a little of this, they added a little of that, or they poured more things together. Why don't we just keep doing that? Why do we need a computer?
Well, that was definitely an art at that time. They were able to accomplish and solve a lot of problems by just applying the art they developed. But today it is a science. We have to understand exactly what is going on when we do a heat treatment to a metal, and it's just obtaining the end result, maybe by luck or maybe by some experience, is not enough today. We have to understand actually what is going on in the metal as we apply this heat treatment to these different metals. And therefore, we use, as I said, the computational techniques and also experimental techniques to understand the theory behind these processes and the electronic, atomic, and microstructural level.
Why do we need a computational component in this materials development?
Well, there are different reasons of using computational techniques in materials development. One reason is to understand the material behavior theoretically. And second reason is have the computational techniques aid us in experimental design. And finally, the third reason is to reduce the amount of money and time spent on experimental work by reducing the number of experiments.
How much time can we save?
Well, that depends on the problem at hand, but that can be sometimes 50% of better or 20% of better. It's hard to tell, but it is definitely it definitely reduces number of experiments one has to make, has to do in order to develop these new materials, and the reason for that is you design the experiments much better and much more efficiently if you have a theoretical understanding of materials behavior. And the computational techniques allows us to have this understanding before we make the experiments.
Using computational technique, would you expect to have a material that was already pretty close in property to what you were hoping it would be, and then you just use the experimental technique to confirm that or improve it?
In some cases, that's true. It is we can come to a ballpark by just computational techniques, and then fine-tuning, if you will, tune it and with experimentation, and that's much more efficient than doing everything with experimentation.
Is one of our goals to be able to move increasingly away from the pouring and melting and more toward computer-based design of alloys so that we minimize the amount of actual laboratory work we do?
That's true. That's true. We today developing materials experimentally only takes a very long time. Sometimes 5 years, sometimes 10 years, maybe longer. And that is unacceptable in many cases because materials are needed much faster. And what computational material science, computational techniques allows us to do is to get an understanding into the materials before actually we make them, and then design our experiments more intelligently, and so that we can achieve our goal at a faster rate. And that is the help we are getting from the computational techniques.
It sounds to me as I listen to you that because we have as a national goal power generating plants that operate more efficiently and with fewer emissions, that we have to have these new advanced materials you're working on in order to actually make those plants be able to come into being. Is that a fair statement?
That's a fair statement. That's very correct. Mm-hmm.
What kinds of efficiency and environmental improvements might we look for with the right materials?
Well, these are the technologies we are targeting here in this lab is mainly fossil energy conversion technologies, and most of the conventional power plants today operates in efficiencies which are between 30 and 40%, and the goal is to increase this efficiency so that we don't burn as much fuel for the same amount of power, and if we can get these efficiencies up to 50 to 60% range, then we would save a lot of fuel and pollute less. So that's the goal that we are.
That's our ultimate objective.
Ultimate objective. Yeah.
Cleaner energy, greater efficiency.
That's right.
That's very good. That's why the Energy Lab is here. Well, thank you for joining us, Doctor. We appreciate you watching Let's Talk Energy that we're doing here from Albany, Oregon at the Energy Lab's Albany site.